G'day guys, just to have a bit of a chat to you about Newton's first law of motion. So there's three laws, but this first one is probably one of the most important to get. So we're going to talk about what it is and some examples of how it works. So essentially, Newton's first law is about how objects, they tend to keep doing whatever they're doing at the time. And we're also going to apply this to a bit of car safety and actually looking at how would you phrase an answer to some real world problems to do with car safety. So starting off with, well, in Newton's first law, an object in motion will stay in motion unless an unbalanced force acts on it. And I'll talk about what that means in a second. So here I've got just a little soccer ball, and this law is easiest to picture if you think about what happens if we're in space. Yeah. So if I have like a person here and they apply some kind of force to this soccer ball to start off with, so they kick the ball and then they apply force and starts getting it moving. And you need to think about, well, what's pushing it now as it moves off into space? It's still moving. And the answer is, well, nothing's pushing it. As soon as an object is in motion, it will stay in motion, and in space there's nothing to affect this object, so it will keep going until the end of time, really. So if you come back 1,000 years from now, that ball will still be there and it will still keep moving, and it will never stop unless there is something to stop it, which logically really makes sense, but that kind of gets obscured a bit on planet Earth, because we have a lot of frictional forces that will change how things move, as opposed to if they were free to move in space. So I've got a bit of a soccer oval over here, and what we're used to seeing is if we set an object into motion, it will actually gradually slow down to a stop, and that leads us to believe that in order to keep an object moving, we have to keep applying a force. And if something's rolling on the ground, that becomes very true, because in fact this object will stop moving because there is an unbalanced force acting on it, and that's the force due to its contact with the grass. So as it's rolling along and moving in this direction, you're actually going to have a force that's going to oppose its motion. So capital F for force there, and it's going to keep acting that way, and it's going to slow the ball down to a stop. So in fact there is a force on the ball that gradually stops it. If we want to keep moving, we have to keep kicking it, basically. We have to keep applying more force. But if we look back to space, if there was nothing there, it will keep going, and that's what you tend to see if you're in an ice rink or something like that, where there's very minimal friction forces to slow down our objects, so they keep doing what they're doing. They maintain their state of motion. Very good. So let's apply this to car crashes, say. So I've got a blue car here, and it's going to face a stop sign, which is hiding behind my face. Let me just grab it out here. So, as your car comes to a stop, if you're a passenger in the car, say, so if you got little Timmy here in the back, what little Timmy will feel as the car's coming to a stop is that he wants to keep moving forward. And that's because as the car's coming to a stop, little Timmy is in motion, so he will want to stay in motion. So you'll find that he actually will start to gradually move forward. But of course he doesn't keep doing that because there's a seatbelt to stop him from doing that and keep him moving with the car. But we can take this to a more extreme case. Let me just get rid of him for a sec. So maybe instead of a stop sign, go away stop sign, the car's actually go on and hit a stovey pole, or like here a lamppost. It's the closest thing I can find. And think about what happens if you're in the front seat and you crash and someone isn't wearing a seatbelt. Well, when the car crashes into this pole, a huge amount of force gets applied onto the car in this direction to stop it, because it was moving this way, in this direction. But if there's nothing attaching the driver to the car, this guy will keep moving at whatever speed the car was moving at. So what happens is he gets flung forwards, and this person's going to hit himself on the windscreen, or herself, and that's going to cause a lot of damage to this person. So it's very important that we have some kind of safety harness, so seatbelt. So just change him to blue. Some kind of seatbelt to keep this person to stop with the car. So quite often you might get physics questions like this: well, why are seatbelts actually needed in a car? And it's really useful to talk about that in terms of, well, what would happen if there was no seatbelt? Well, if there was no seatbelt, what that means is a collision means that the passengers in that car stay in motion. They don't stop with the car because there's nothing to stop them. So that means they go and hit the windscreen and they're going to injure themselves. So what the seatbelts actually do is they provide this thing called an unbalanced force that is needed to slow them down. Otherwise they're going to injure themselves. And you can imagine a seatbelt provides a bit more support than a windscreen in stopping a person. So we've talked about what happens if an object is remaining in motion, but the reverse is true as well. An object at rest will tend to stay at rest, and you will have experienced this if you're, say, on a train and the train suddenly accelerates. So we've got green light here on the train, it's time to go. And let's say you're on the train and you've neglected to actually hold on to something as it starts moving. I'm not going to draw the people inside here because it's a bit small, so I'll just draw people on top. Okay, so there's someone. So what happens is that as the train starts moving, well, the engine of the train can apply forces to itself to start it moving, but this person is not attached to the train, so from his or her perspective it feels like they're falling backwards, when actually it's like the train is being lifted out from under them. And that's why you feel a sudden, like, if I was on a train and it was moving that way, if it starts moving, I'll go, and I would start falling over because it's like the train is trying to move away without me, so I need to hang on so I keep moving with the train. A classic example of this is what I'll show you next. Just give me a sec. So a classic example would be the tablecloth trick. So I've got some objects here, and, well, not a tablecloth, but close enough, a piece of paper. So if I whip this fast enough, these objects are at rest, and they should remain at rest because I'm going to apply this force so fast that it's not going to transfer to these objects. So hopefully they should remain at rest if I whip it fast enough, like that. So you've got two objects that are at rest, okay, and they're going to remain at rest if no force is going to try and move them. So we can whip out a tablecloth and those objects stay there at rest. Now if we take this idea, objects at rest need to stay at rest, and apply it to car safety, I want you to picture you're in this car here, the blue car, and this red car doesn't quite see the stop sign here. Perhaps they were looking at their phone, and here they come, and they crash into this car. So if you're inside this car, it's actually going to have a bit of a shunt forward as this red car crashes into it. And that's very bad news if there's no headrests in the car, for example, because what's going to happen is that a force is pushing this car forward, so like the chair and yourself, so the chair is going to be moving forward, but the car at the back's pushed it, so your body will move forward with the chair, but hang on, there's no headrest, there's nothing to push the head, so the head's going to stay at rest, and oh my gosh, that's going to cause some damage to the neck there, so it's very, very bad. So that's why we actually need a headrest here, so I'll put a headrest in for this person. There you go, give me nice and red. So that way you can actually push the person's head so they can move with the car and they can be safe and save some damage to their neck. So why are headrests in your car? Well, again, we can talk about what happens if there isn't any headrests. Well, that means if a car hits your car from behind, the head of a person driving that car is stationary, so it is going to stay stationary. But if the person's body is travelling with the car, it's going to cause stress on the neck, as it almost gets pulled out from under the person, and their head will actually get bent backwards because it's trying to stay at rest. So a headrest then provides the unbalanced force needed to change the motion of your head, and it needs to move with the car, so it doesn't actually get damaged. That's why it's so important. So in summary, if we have an object in motion, it's going to stay in motion. If there's an object at rest, it will stay at rest. And that will happen unless an object has an unbalanced force acting on it, and that can actually change what the object is trying to do, and change how it's moving or not moving, as might be the case. And that's it for this time. Thank you very much.